Let's talk about mass balance in chemical reactions. This is balancing chemical reactions. The law of conservation of mass says that matter is neither created nor destroyed during a chemical reaction. What this means is we have to have the same number of each type of atom on the left side of the equation when we're starting the reaction as we have on the right side of the equation when we finish it. So here are some rules for balancing equations. First, we have to begin with a formula equation, and it's really important that you have the right subscripts on all your chemical formulas. So for a covalent compound, make sure your prefixes are reflected in the subscripts of the compound. For an ionic compound, make sure that you have balanced the charges on the cation and on the anion. Once you have that formula equation with your subscripts, don't change them. You can't change the subscripts. That changes what molecule it is, and the identity of the compound is different, so we can't do that. What we will do is we'll use more than one of each of the different types of molecules in order to come out with an overall balanced equation, and we'll use coefficients to represent that, and I'll show you what that means. So let's take a look at hydrogen gas. So hydrogen gas reacts with oxygen gas to form water vapor. So I have H2 as a gas reacting with O2 as a gas to form H2O as a liquid. These two are both diatomic molecules. They're part of that 7+1 group. So since they're not combined with anything else, they have to have a subscript of 2. Represented pictorially, I have 2 hydrogens in my H2, 2 oxygens in my O2, and then I have H2O, 1 oxygen and 2 hydrogens. Looking at this right now, I have 2 hydrogens on the left and 2 on the right, but while I have 2 oxygens on the left, I only have 1 on the right. And so we need more oxygen on the right. And we have to bring an entire another molecule of water along. We can't just add an extra oxygen. We don't find that in real life, and so we can't create things that don't exist when we're balancing our reactions. So instead, what we're going to do is we're going to add a whole nother molecule of water. So H2O. That fixes my problem and the fact that oxygen was not balanced. Now it is. I've got 2 oxygens on the right and 2 on the left. I have, however, messed up the balancing for our hydrogen. I now have 4 hydrogens on the left, only 2, or 4 hydrogens on the right, only 2 on the left. And so I need to add 2 more hydrogens to the left side of this equation. By doing so, I fixed it. I have 4 hydrogens, 2 oxygens, 1, 2, 3, 4 hydrogens, and 2 oxygens. So my picture is great. I now need to reflect this in my chemical equation, and I'm going to use coefficients, which are numbers in front of the chemical formulas. I have 2 hydrogen molecules that I need, so I'm going to put a 2. And this means I need 2 of the H2 molecules, like I have here. I only need 1 oxygen. You can write a 1 if you want, but it is implied, so we don't usually do that. I have 2 H2O molecules. I need to write a coefficient of 2 in front of my H2O. And now I have written a balanced chemical equation. If I take a look at another example, this one we're going to start from a word equation. I have solid mercury 2 oxide decomposing to form liquid mercury and oxygen gas. Okay, we have to start by writing our proper formulas. Mercury 2 oxide. Well, mercury's Hg. That Roman numeral 2 indicates its charge is +2. It's reacting with oxygen, and the charge on oxygen in an ionic compound is generally -2. Those charges +2 and -2 cancel. I don't need any subscripts. And I said it was a solid, so we can put that on there. It's decomposing, which means it's breaking down. It's not reacting with anything else. It's just going to break some bonds. And it's going to form liquid mercury and oxygen gas. Again, oxygen is a diatomic. Since it's no longer combined with another element, you have to have a subscript of 2. When I draw a picture of this, I have mercury and oxygen, because those both have a subscript of 1. I have a mercury, and then I have my O2. Right now, oxygen's not balanced. I have 1 on the left and 2 on the right. So I need more oxygen on the left. I have to add a whole nother molecule of mercury oxide. That's how it comes. So I'm going to add a whole other molecule of mercury oxide. That fixes the oxygen problem. Now I need to address the fact that by doing that, I have 2 mercury on the left side, only 1 on the right. So I'll add another mercury and check myself. 1, 2 mercuries on the left, 1, 2 mercuries on the right, 1, 2 oxygens on the left, 1, 2 oxygens on the right. Beautiful. So let's now reflect that with coefficients in my balanced chemical equation. So I'll put a 2 in front of my mercury oxide because I needed 2 molecules, a 2 in front of the mercury because I needed 2 mercuries, and then just 1 oxygen is all that is necessary. Again, I can write a 1 or not. It does not matter. Okay, one last example. Potassium chlorate, which is a solid, decomposes upon heating to form potassium chloride, another solid, and oxygen gas. So we're going to again start by writing my formula equation. So I've got potassium chlorate. Potassium is K, chlorate is ClO3. You have to stop and check that your charges cancel. Potassium's +1, chlorate is -1. And so this is balanced. I don't need any additional subscripts. That was a solid. It's decomposing to form potassium chloride solid. Potassium is +1. Chloride is -1 as well. So that is no subscripts are needed. And oxygen gas, O2, my diatomic oxygen again, as a gas. Instead of drawing pictures for this one, we're going to make a little table. And it doesn't matter which method you prefer. My table is going to contain all the different elements in the entire equation. So I've got potassium, chlorine, and oxygen. In the potassium chlorate, on the left side of this equation, I have 1 potassium, 1 chlorine, and 3 oxygens. So 1 potassium because of the subscript, 1 chlorine, and 3 oxygens. On the right, I have 1 potassium, 1 chlorine, and 2 oxygens. So my oxygen doesn't balance. Because these have to come as complete units, I can only add O2s on this side and KClO3s on this side. The smallest number of oxygens that I can get on both sides of the equation is the least common multiple of 2 and 3. It's back. And that is 6. And so if I'm going to get myself to 6 oxygens, that would require 3 O2 molecules. They come in groups of 2. To get to 6, I would need 3 groups. And so what I will do is I'll say, well, if I put a coefficient of 3 in the front, that gets me 3 groups of O2s. And so I would now have a total of 6. You multiply the subscript by the coefficient to figure out your total number of any particular atom. And then I'll put a 2 in front of KClO3 because 2 times 3 gets me 6. Now when I added this 2, it affects the entire molecule. So I now have 2 potassiums and 2 chlorines as well. 2 potassiums and 2 chlorines. Which means while I fix the oxygen, in the process I impacted the balancing of potassium and the chlorine. So on my potassium chlorate, I need 2 of those. Let's add a 2 in front of the potassium chloride as well, because that would get me 2 chlorine or 2 potassiums and 2 chlorines. So now everything is balanced. And so the table is an alternative way, instead of drawing pictures, of keeping track of how many of each element that you have and ensuring that you get to a balanced chemical equation.